Let's start Basic Lecture 1. In this lecture, you will learn about the geometry and radiation source definition. The goal of this training is to understand the basic format of the PHITS input file, set the basic system and radiation source, and be able to execute particle transport simulation. This is the simulation result at the end of this training. It shows the particle fluence in the system when a 290 MeV proton beam is incident on a cylindrical water. The contents of the training are shown here. The order of the contents of this training will be general description, geometry, source, summary, and homework. Here is the format of the PHITS input file. All calculation conditions are described by text input. The input file consists of multiple sections, and the section name in square brackets indicates the beginning of the section. The basic format of the input file is represented by a keyword or parameter equal to a numerical value or a character string. At this time, the space is ignored. Alternatively, it is represented by a list of numbers or character strings. At this time, please note that it is separated by spaces. Up to 200 characters can be put on one line, and more than that, it should be on the continuation line, and the continuation line should have 6 or more spaces at the beginning of the sentence. It is also possible to give parameters as mathematical formulas. Here is the input assistance. By turning off the section name, you can skip the section. When you write QP: at the line head, reading of parameters is skipped from this line to the next section. Q: is equivalent to the end section. Any input information written below the end section is ignored. To add a comment in an input file, please add C in the first 5 columns of a line except the material section and $ and hash in the middle of a line. But please avoid using hash in the cell and surface sections. Considering the above, we recommend using the $mark for comment marks. Here is shown the main components of input file. In the PHITS simulation, geometry in 3-dimensional virtual space and information on source particles are both essential to tally various quantities of the particles. They are 3 fundamental components. Please open and see input example of Lec 01 INP. This slide shows the configuration of the sample input of Lec 01.INP. This input file consists of 9 sections. The material, surface, and cell sections define the 3-dimensional virtual space. The source section defines the production of particles. The track tally and 3D show tally define the observation of quantities. Here, the file obtained by the calculation of this example is shown. Batch.out shows the progress of the calculation. Details will be explained in Basic Lecture 3. PHITS.out shows a summary file of PHITS calculation results. I will briefly introduce it later. The remaining files are image and numerical data files of calculation results and statistical errors. Details will be explained in Basic Lecture 2. Here is an example of terminal output. It includes input file name and calculation progress and time information. If there is an error in the input file, error information may be output. This is an EPS file that shows the image display of the calculation result and a summary file that shows the summary of the calculation. Here is the standard output file. The first part of the PHITS out file is PHITS logo and version information. The second part is the input echo. In this part, parameters specified in the input file are shown with description of the parameters and their default values. The third part is the memory status, in which you can check how many memories are used in the calculation. The fourth part is the batch information. And the last part is the summary of PHITS simulation. In the last part, you can check these information, that is, numbers of events such as source generation and nuclear reaction, information on transported particles, numbers of secondary particles, CPU time, and numbers of library data access and use of reaction models. It should be noted that error information is mostly given in the console window, but occasionally in the output file. This indicates the section type. Various sections are provided to faithfully reproduce the actual experimental conditions. Please see Section 5 of the manual for each section. Here is shown the list of tally. Several tallies can be defined in one calculation to obtain various information on the particle transport. The detail for each tally section is described in the PHITS manual, and it will also be introduced in the basic lecture number 2. Next is general definition of geometry. Here is shown general definition of geometry. To make a three-dimensional geometry, following 3 steps are required. First, you define materials in materials section. Second, you define surfaces of cells in surface section. And then, you define cells by combining of material and surface in cell section. In the PHITS calculation, cells are defined in XYZ coordinate system. You can use an infinite space. However, void and air regions have to be defined explicitly. Furthermore, the outer boundary of the virtual space, so-called outer void, has to be defined. The outer void work as a cutoff region, that is, when particle enter the outer void, transport calculation of the particle is finished. Here is shown how to define materials. The format of definition is material number, symbol for element, and composition ratio. For example, this line defines 2 hydrogen and 1 oxygen, that is water, for material number 1. You can define composition ratio as atomic ratio and mass ratio by changing sign of ratio. Positive composition ratio means atomic ratio, and negative composition ratio means mass ratio. It should be mentioned that when elements are specified without mass number, natural isotopic composition is assumed. Following formats are available to specify the mass number. You can use element symbol with mass number and formula with atomic number and mass number. Now let's see how to define a surface. The format of definition is surface number, shape and parameters. For example, this line defines surface of sphere having its center at the origin of the XYZ coordinate system with a radius of 10 cm. Note that parameters are in units of centimeter. There are various types of surface shapes, that is, sphere, plane, cylinder, rectangular, and so on. Next slide shows how to define cells. The format of definition is cell number, material number, density, and surface numbers. For example, this line defines the cell with the number of 100, which filled by water with the density of 1.0 gram per cubic centimeter, and the region is inside surface 10. When material density is over 1, the unit of atom density is 10 to the 24 atoms per cubic centimeter. When material density is less than 1, the unit of atom density is gram per cubic centimeter. The next line defines cell number, the outer void cell, and outside surface 10. When you define void, density is not necessary. Now, let's confirm the geometry defined in the input file. Please open the LEC01 INP file by your text editor. The procedure to confirm your geometry is as follows. At first, change ICNTL parameter in the parameters section. Please set 8 for eye control when you confirm the geometry. Next, overwrite save the input file and execute PHITS. After that, open an EPS file track XZEPS, and you can see like this figure. Let's start exercise 1. In this step, please change the radius of the sphere to 20 cm. The left side shows a part of input file, and the red underline points the parameter that have to be changed. After editing the input file, please execute PHITS and check the output file. Please start the exercise. Here is the answer. The cell 100 is defined by surface 10. So we change the radius of the surface from 10 cm to 20 cm. After that, you will obtain this result. This slide shows example of error message from input file. If you fail to run PHITS, the line number where the mistake was made and its contents are displayed in the terminal window. It may be output to PHITS out. In this case, please check the contents of the corresponding line number and correct the input file. Here is shown about the input file. Every lecture of PHITS tutorial has a lot of exercises, but only one, or a few, input files are included in each folder. If you would like to skip some exercises, you can use the input files in input folder, such as LEC1-2 INP. For example, if you would like to try the exercise 3, please use LEC1-3 INP in the input folder. This input file includes all the revisions that have been done in the exercises 1 and 2. In this slide, let's define a new surface. Please define a spherical surface whose radius is 5 cm and center is at the origin of the XYZ coordinate system. The surface number of the new surface is 11. In this step, we just define the surface, thus geometry does not change. In the exercise 2, please add a new spherical water cell with 5 cm radius to the system. Let's use 102 for new cell number. Let's start with this exercise. If you defined the cell 102 like that, you obtained the result as shown here. This is because part of cell 100 overlaps cell 102. The overlapped regions is painted in black. This is one of typical errors in cell definition. PHITS always identifies the region in which the particle is crossing, so PHITS get confused when one location is doubly defined. When a geometry error occurs, PHITS outputs an error file to provide detailed information on the error. The contents of error file is shown here. There are cell numbers. Error is observed there. These are X, Y, Z coordinates where the geometry error occurs. Information at multiple coordinate points is exported even if only one error has occurred. The other type of geometry error is undefined region. Geometry is defined in an infinite space, but every single point must be filled with certain materials or defined as a void. Undefined regions is painted in purple. If undefined region is present, the other region does not appear sometimes. Next, proceed to the method of defining cells. The topic of this subject is how to define cells. Cells are defined by surface using plus and minus signs and Boolean operators. At first, plus sign on the surface number means the outside of the surface, and minus sign means the inside of the surface. Boolean operators are used when you define cell by combined use of more than two surfaces. The detail will be shown in the next slides. Here is shown the Boolean operator, AND. To define a cell inside or outside of two surfaces, connect the to number with a blank. It means and. So, in the case of exercise 2, the cell 100 are defined by inside of surface 10 and outside of surface 11. And then we will obtain the answer as shown here. So please try and check it. Next, here is shown the Boolean operator not. When you want to exclude cells from the other cell, you can use hash mark. It means not. You can define cell 100 by using not, like that. It means the cell 102 is excluded from the inside of the surface 10, thus they are equivalent. It should be noted that cells are usually defined by using surface number, but hash mark must be followed by a cell number. When you use surface numbers with hash mark, you have to set surface numbers inside round bracket. This will be explained later. Before we go on the next exercise, we will extend the virtual space. Three-dimensional virtual space should be large enough to contain all the geometrical components. So, let's change the radius of surface 102 to 500 centimeters. After that, you will get the result like this figure. Now, let's start exercise 3. In this exercise, we will add sphere cell 103 having its center in the XYZ coordinate 0, 0, 11 with radius of 5 centimeters. Here, the symbol for surface shape is SZ when you define the sphere on the Z-axis. So please execute and check where is cell 103. Let's start it. The cell 103 will placed on the right side of cell 102. Here, spheres are defined with symbols of SX, psi, and SZ when center of sphere is placed on the axis. The universal expression S is used with the XYZ coordinate of its center and its radius. In the next exercise, we will change the center of cell 103 inches to Z equals 8 inches. When the cell is moved, two spheres are overlapped and geometry error will occur. So please exclude this overlap regions from cells 102 and 103 and create a new cell 104. Here is shown an example of the answers. Cell 104 is added, and it defined inside of surface 11 and surface 12. These surfaces are excluded from both cell 102 and cell 103. Cell 104 is also excluded from cell 100. Newly added cells have to be excluded from the background cell. Here is shown the Boolean operator, OR. To define a sum of two regions as a cell, connect the two numbers with signs by colon. It means OR. It is an example for excluding cell by using colon. These expressions give same result. It should be mentioned that you have to use surface numbers inside round bracket after hash mark. Here is shown a bad example using unnecessary hash marks. This is an onion geometry, which are constructed by 5-sphere surface, like onion. If you define this geometry by using hash mark, input file becomes long, while input file can express simpler by using and or operators. Next is definitions of boxes and cylinders. This slide shows how to make a box. Boxes can be defined using RPP, which is rectangular parallelepiped. This surface needs 6 parameters to set minimum and maximum of XYZ coordinates. Please note that RPP is defined in the surface section because RPP corresponds to 6 surfaces of the box. Let's start with exercise 5. Now, let's define a 10 cm cube centered at 0, 0, -11 using symbol of RPP. First, Set a cube in the range of -5 cm to 5 cm for x and y directions, and -16 cm to -6 cm for z direction. Then, in the cell section, define the inside of the surface specified by RPP as a cell using a minus symbol. Let's execute PHITS and see the result to confirm whether a cube is correctly defined or not. Here is the answer. At first, RPP surface is defined in surface section. And then, cell 105 is defined as an inside of surface 13, and this cell is excluded from cell 100. This slide shows you how to divide cells by a plane. In the surface section, we can also define plane. The symbol of px means perpendicular plane to x-axis. The numerical parameter of px means where the plane is placed on. In the cell section, we use symbols plus or minus to distinguish the two regions divided by a plane. So, now, let's add red texts and then execute PHITS. This is the result. The cell 102 is defined as an inside of the surface 11, and outside of the surface 12, and negative region of the surface 14. That is, the positive region of the surface 14 in the sphere with the 5 cm radius is cut. Py and Pz are also available. Be careful of the meaning of plus and minus when you use planes. Here is shown how to make a cylinder. A cylinder is defined using an infinite cylindrical tube and two planes. Now, let's define a cylinder in exercise 6. Please add red texts in the surface and cell sections. In the surface section, symbol of CZ means parallel cylindrical tube to z-axis. The numerical parameter of CZ is the radius of tube. In the cell section, please define a cylinder as a cell 106. The inside and outside correspond to minus and plus symbols, respectively. Since the cell 106 overlaps the cells 100, 102, 103, 104, and 105, new cells should be excluded from these cells. Let's execute PHITS and see the result to confirm whether a cylinder is correctly defined or not. Here is the answer. Cell 106 is a cylinder with a radius of 1 cm and a height of 38 cm. And the cylinder 106 pierces all regions. For cell and surface definition, we recommend to rearrange cell and surface numbers according to own rules. For example, rearrange the numbers in ascending order in each plane surfaces. Next is shown how to add materials. In this subject, we learn how to add materials. You can add a new material number and define a composition ratio of the material in Material section. Please note that the density is given in the cell section. When you write symbol of element without atomic number, its natural isotope ratio is used. We can also define mixtures and compounds as shown here. Now, let's start the exercise 7. Please add copper in the material section, and change the material in the cell 106 from water to copper. The density of copper is 8.93 gram per cubic centimeter. At first, define the material number 2. And then change the definition of cell 106. Note that each material number has own color. After that, please execute PHITS and check the result. Here is the answer. At first, copper is added in the material section. When you write symbol of element without atomic number, its natural isotope ratio is used. Next, the material number and density for cell 106 is changed. And then you get this result. Let me go on the next slide. Here is shown how to make a void cell. The material number for void is 0, and material number for outer void is -1. When you set void cells, the densities should be skipped. So please define the cell 100 as void, and then execute PHITS. The right figure is the result. You can see that color of cell 100 changed. With the Material Name Color section, you can change the colors of cells and specify the name and color of each material number. Let's add Material Name Color section in LEC 1 INP and execute PHITS. After that, you can obtain this figure. This slide shows the color definition. You can use these colors in the Material Name Color section. Next is shown geometry drawing software. This slide shows about confirmation of geometry with Fig 3D. Here, Fig 3D is PHITS Interactive Geometry Viewer in 3D, which is an input geometry visualization software for PHITS. Let's see the geometry by using Fig 3D. For Windows, we can right-click the PHITS input file and select Send to and Fig 3D. For Mac OS, we can drag and drop the PHITS input file to the Fig 3D icon in the dock. For Linux, we can move to the folder with the PHITS input file and type Fig 3D PHITS INP in the terminal. Here is how to cut of a cross-section with an auxiliary plane. Click the Settings tab to display the auxiliary plane display. X, Y, and Z are planes perpendicular to the x-axis, y-axis, and z-axis, respectively. Select Enable or Disable for cutting plane in the checkbox. You can also select Cut of the plus side, minus side with the radio button. Finally, press the Draw button to display the cross-section in this figure. Here is how to select cells for visualization. When you click the cell pane, the list of cells is displayed. When you uncheck cell 102 and click the Draw button, the material of cell 102 is disappeared. Here is shown how to change the colors. First, please select Tools Configuration Color in the menu bar. Then, you can select colors of background or materials in the Color tab. After that, click the OK. These setting parameters correspond to the Matte Name Color section. Changing the colors is also available with a Matte Name Color section. Here is shown Super MC. It is a free software developed by the FDS team at the Chinese Academic of Science. Registration is required when you get it. It converts CAD geometry into several Monte Carlo code format. Compatible CAD formats are SAT, SAB, STP, and STEP. The sample of Super MC and PHITS are placed in this directory, but instruction only available in Japanese at the moment. From here, let's learn how to define radiation source. To define the radiation source, we have to set the source section. This is the second main component of the PHITS input file. Here, types of sources are shown. PHITS has several source types. So, we have to select the type in accordance with each purpose. For example, point isotropic source is suitable for simulating radioisotope facilities. For accelerator facilities, pencil or broad beam along specified direction or cone beam source is suitable. For radioactive waste and internal exposure, volume isotropic source should be set. For cosmic ray and external exposure, isotropic irradiation within certain area is used. In this slide, 4 points to define the source section are shown. The first one is shape of source distribution. This means spatial distributions. Point, cylinder, sphere, etc. are available. Next is energy of source particles. Mono energies or continuum spectra can be set. The third one is source particle species. We can set neutron, photon, proton, heavy ion, etc. The last is direction of source particles. Isotropic, directional, cone shape, etc. can be set. Let's see the source section of lec01.inp. The source section is used to define the source particle of the simulation. The first parameter is S-type. When setting S-type equals 1, a cylindrical shape is set as a region for generating source particles. What information is required to define a cylinder? Parameters in the blue line box are used to define a cylinder shape. This slide shows several parameters to define a cylinder source. First, the default direction of PHITS is +z. So, a central axis of the cylinder is z-axis. R0 is a radius of the cylinder. Z0 and Z1 are, respectively, minimum and maximum of z coordinates. The height of the cylinder is determined by these parameters. X0 and Y0 are, respectively, x and y coordinates of the central axis. These parameters are optional, and their default values are 0. R1 is also optional. When you set this parameter, the inner region is removed, and then the source region like pipes can be set. When setting S-type equals 1, we can define not only cylinder shape source but also circle and point shape sources. In this slide, red arrows mean directions of source particles. When we set isotropic source, the directions are randomly determined like this. The center and right figures are examples of extension of the cylinder shape. When you set Z0 equals Z1, for example Z0 equals 5 and Z1 equals 5, the shape of the source becomes a disk. Furthermore, by setting R0 equals 0, the shape of the source becomes a point. Note that source disks or points should not be set on boundaries of cells, because numerical errors sometimes occur when running a PHITS simulation. Let's try exercise 8. Execute a transport calculation of PHITS. Please change I control parameter to 0 in the parameters section. Check R0, Z0, and Z1 parameters in the source section. These settings mean point source at the origin, 0, 0, 0. Furthermore, please check the T-track section too. Although we will learn the detail of this section in the second basic lecture, here, please set NT equals 10, and then execute PHITS. This T-type setting gives output of transport simulation of 10 pages. After running PHITS, please open the track.xzfs file. Each page means an output of the transport simulation from 0 to 1 nanosecond in 0.1 nanoseconds increments. This is answer of the exercise 8. This red line in track.xzfs means trajectory of source proton particles. These protons were generated at the origin, and then moved along the z-axis. Their direction is +z, and the length of this trajectory is short because proton is a charged particle. Next, let's make a disk source with a radius of 1 centimeter. In this case, please change R0 parameter. This is answer 9. By setting R0 equals 1, the width of the red beam was spread out. Because the radius is 1 centimeter, the width is 2 centimeters. Next point is energy setting of source particles. Mono energy can be defined by E0. It should be mentioned that the unit of energy is MeV per nucleons. Please remember this unit is important for heavy ions. Of course, this is MeV for protons or neutrons. When we set energy spectrum, the distribution is defined by E-type subsection. This subsection is not explained here, but we can learn it in Source A of the advanced lecture. The third point is source particle species. By projectile parameter, we can define the particle species. We can use symbol or KF code to define it. This table shows the symbol and KF code for each particle. The symbol format is usually used in the definition. Nucleus is specified by mass number and element symbol, for example, 12C for carbon-12 ions. It should be mentioned that when we use radioisotope sources, we have to specify the emitted particle species, such as photon. KF code is special expression in elementary physics. This is not used usually, but we have to use this format, for example, when simulating neutrino transport. Next is exercise 10. Let's change the source particle to neutrons with energies of 100 MeV. We can solve this problem by changing PRA and E0 parameters. This is answer 10. By setting PRA equals neutron and E0 equals 100, we can obtain the result of the neutron source simulation like this. These neutrons can penetrate the material unlike protons. The last point is direction of source particles. The direction is defined in the spherical coordinate system, and z-axis is the default direction in PHITS. The parameter dir means polar angle, phi means azimuthal angle, and dom means beam spread. The main parameter is dir. This is cosine of the angle between the pointing direction and the z-axis. Therefore, dir equals 1 means the angle, theta, equals 0 degree, or dir equals 0 means that theta equals 90 degrees. As a special setting, dir equals all means isotropic source. Next slide shows how to set phi parameter. Phi is azimuthal angle, and is given in units of degrees. Please be careful this unit because that of dir is different. Phi is given as counterclockwise angle between the plus x-axis and the projection onto the xy plane. For example, when we set the direction tilted by 45 degrees from the plus x-axis on the xy plane, we have to set dir equals 0 and phi equals 45. The last one is DOM parameter. DOM means solid angle. The unit is degree. When we define a beam spread of 30 degrees, we should set DOM equals 30. Here is shown the relation of parameters dir, phi, and DOM in the spherical coordinate system. Let's move on the next exercise. Please define an isotropic point source at the xyz coordinate 0, 0, 10. Please change 4 parameters above red lines. When S-type equals 1, we can define an isotropic source by setting dir equals all. This is answer of the exercise. The answers are dir equals all, R0 equals 0, and both Z0 and Z1 equal 10. Please see the right panel. We can find that the red point is at the coordinate 0, 0, 10, and the direction of the neutron source is isotropic. So let me summarize the basic lecture number 1. This is summary of the basic lecture 1. The main components of a PHITS input file are geometry, source, and tally. Geometry is defined by the 3 sections, material, surface, and cell sections, and we can define various 3D geometrical components based on the GG, general geometry concept. Source is defined by 4 points: shape, species, energy, and direction of particles. Tally is used to calculate the quantities in PHITS radiation transport calculation. This will be explained in the basic lecture 2. Let's try this homework. Please use an input file, Homework 1 INP, in a folder shown in this slide. In this homework, we have to make a water cylinder and then irradiate it by a proton beam at 290 MeV. There are several hints in these slides. Please try this problem step by step.